Welcome to the first lecture on Chapter 5. Today we are going to talk about gases and gas properties. So not only is, our gases important because of the oxygen that we breathe in, but we have a lot of uses for gases just in our daily life. For example, gases keep you safe. If you think about, your airbags, if you were to get in a car accident, right, you have airbags in your car. And that airbag is a really rapid decomposition reaction. You have this compound, this sodium azide, which is stored in an airbag. And when it, gets hit, it is a contact explosive. It's contact reactive. And when it gets hit, it undergoes a rapid decomposition to produce sodium and nitrogen gas. And when it produces that nitrogen gas really, really quickly, that nitrogen gas fills your airbag and keeps you safe, which is really cool. So there's a lot of properties of these gases that are really important to our daily life. So here are some properties of gases. So gases will expand completely to fill their container. They will fill whatever container you put them in completely, right? If you think about the oxygen in the room doesn't just all stay on one side of the room. It spreads and it fills the container completely. Okay, or fills the room completely. It will take the shape of their container. So for example, balloons. If you pump some helium into a balloon, it will take on the shape of the balloon. Helium doesn't have its own shape. It will take on the shape of whatever you put it in. It has a very low density, much less than a solid or liquid. For gases, we typically will measure the density of gases in grams per liter, whereas we were measuring, solids or liquids in typically grams per milliliter or grams per centimeter cubed, which end up being the same thing. So it's a much lower density. Gases are compressible. So if you've ever gone, paintballing, right, you will buy a CO2 cylinder, and that is compressed carbon dioxide. Okay, it is under very high pressure, so that means you can keep, adding and adding more gas to the same container, and it will still, be able to fit in there. We can compress it. Mixtures of gases are always homogeneous. So like the air that we breathe, that is a homogeneous mixture. And it's not just oxygen, right? It's also got, nitrogen, and it's got a lot of other things, carbon dioxide, all kinds of stuff. And gases are fluid. So a lot of times when we think about the term fluid, we think about liquids, right? Because you can pour them and they flow, but gases flow as well. Like if you think about a gas flowing through a valve, or if we think about the balloons, again, the gas will flow out through that opening. Gases are fluid. They do flow. So we're going to talk a little bit about kinetic molecular theory. And our kinetic molecular theory is our way of thinking about gases. Because gas particles are really small, and so this kinetic molecular theory is a series of assumptions to let us think about how the gases behave. So the particles of the gas, whether that's atoms or molecules, they are always constantly moving. They are in constant motion. And like we've talked about before, this is true for all atoms, right? Whether it's particles of a liquid or particles of a solid, your particles are always moving. Whether they're vibrating in place or flowing through the air, they're always moving. But these gas particles are moving quickly. The attraction between the particles is negligible. So when we have these gas particles, what that means is that the gas particles are kind of zooming past each other, and they're not going to experience any attraction or repulsion from the other gas particles. So they're all acting independently. They're all doing their own thing. And then when the moving gas particles hit another gas particle or the walls of the container, they do not stick. They bounce off and then continue moving in another direction. Okay, we call this an elastic collision if you've taken physics already. There is no energy that is being lost in these collisions. They're simply going to hit, the other particle or hit the sides of the container, and they will move on. You can think of them like billiard balls. Like if you go to play pool, right, you hit that white cue ball, and then it's going to hit, the blue one, and it's going to, bounce off. Okay, we're not having any loss of energy in that collision. So another aspect of kinetic molecular theory is that there's a lot of empty space between the gas particles, right? The gas particles themselves are really, 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 really small, and there's a very large distance in between them. So we are actually going to say that under kinetic molecular theory, we are going to assume that the volume of the particles themselves are 0. We are going to think of the gas particles as having absolutely 0 volume. Now, in reality, that's not true, right? The atoms and molecules do take up some space, but because they are so small compared to the space in between them, we are going to say that they have a 0 volume. And this is actually going to make our calculations much, much easier because we don't have to take into account the size of the particles themselves. And the average kinetic energy is going to be directly proportional to the Kelvin temperature. Okay, so be very, very careful. Whenever you're doing calculations with gases or you're talking about gases at all, you need to convert all of your temperatures to Kelvin. So whether it's in Celsius or Fahrenheit, doesn't matter, you need to convert it to Kelvin. But the average kinetic energy of the gas particles is directly proportional. And our kinetic energy is our energy of movement. So what this means is that as you raise the temperature of the gas, right, that means that your particles are going to move faster. Okay, the average speed of the particle increases. Okay, this doesn't mean, though, that all of the gas particles are moving at the same speed because they're at the same temperature. We're also going to look at the size of these gas particles and a Boltzmann distribution and things like that. But this means on average, right, as you increase the temperature, your gas particles will move faster. Okay, so gases have indefinite shape and indefinite volume. And this is because, right, the gas particles have enough energy to overcome the attractions that are holding the particles together. Normally, if you think about a solid or a liquid, right, the reason that they're not moving very far, right, those particles are just kind of vibrating in place, is because they have these strong attractions that are holding the particles together. So the stronger attractions will be found in a solid, like ionic bonds are very strong. Those attractions between the positive cations and the negative anions, that is a really strong attraction, and it's holding those particles together and keeping them in a solid. As you decrease the attractions a little bit, then they can be a little bit more fluid, like a liquid, and they can flow, but they're still being held, kind of tightly in place. They're not able to escape. The gas particles have very low attractions between the atoms and the molecules, and so they do not have to stay in their place. They can move about independently, and they will keep spreading and moving until they fill the container. And as a result of this, gases will take the shape and volume of any container that they are in because they have no, loyalty really to the other gas particles. They're all moving independently and doing their own thing. Okay, because there's a lot of unoccupied space in the structure of a gas, the gas particles themselves don't have a lot of mass, then we have a really low density, right? So if we think about density, grams per liter, right, the gas particles themselves are going to be really, really light, and they are spread out a lot. So the gas, our grams is going to be a very small number, our liters is going to be a very large number, and so we're going to end up with a fairly low density. Those particles are very far apart in a given volume. Okay, pressure. Pressure is one I want to spend a lot of time talking about, and we are going to talk about pressure in terms of collisions. Okay, so anytime you hear pressure when we're talking about gases, I want you to think about collisions. What are the collisions doing? How many collisions are there? Are the collisions increasing or are they decreasing? So always about collisions. And if you think about like a ball, if a ball hits a wall, it is exerting pressure on the wall, right? Because it hit it. So we're going to think about our gas particles this same way. When the gas particles hit the walls of the container, they are exerting pressure. And this is how we are going to measure pressure. Okay? The result of all of these little collisions, right? All of the molecular collisions with the walls of the container, that is going to be how we're measuring pressure. And pressure is going to be force over area. So we're looking at essentially how many collisions there are over a given area. Okay? This is kind of a physics definition, right? Pressure is force over area. Again, this is, how it's defined, but we're going to think about it in terms of collisions. Are we increasing collisions or decreasing collisions? Okay, so gas pressure is a result of the constant movement of the gas particles and their collisions with the surfaces around them. And the pressure of the gas depends on several factors: the number of particles in a given volume, right? If you have higher number of particles, then you're going to have more collisions, which will be more pressure. If you have fewer particles, then you're going to have fewer collisions and less pressure. The volume of the container also matters, right? If you put a ton of gas particles into a really small container, then they're going to hit the sides of the container very frequently. If you put, just a couple gas particles in a very large container, then you won't have very many collisions with the walls of the container, so we're going to have a lower pressure. And then the other one is the average speed of the gas particles. If the gas particles are moving faster, they're going to hit the walls of the container more frequently. If the gas particles are moving slower, then they will hit the walls of the container less frequently. So the way that we measure pressure is we can use an instrument called a barometer. And so this is an example of a really early barometer, and it was developed by this guy named Torricelli in 1643. And the way that it works is you would have this pool of mercury down here on the bottom, and we would put a glass tube, kind of like a test tube, and we would suck out all of the air, right? We would make it a vacuum, and then we would stick it upside down in the mercury. And what happens is that the atmosphere, right, is pressing down on the mercury. And we don't think about the atmosphere pressing down on us all that much, but if you think about it, right, there are particles that are constantly colliding with you and, sitting on top of you because there's a good amount of atmosphere on top of us. And so there is a lot of pressure that we're experiencing, but since we're used to it, we don't really, think about, okay, there's a ton of pressure sitting on top of us. But if you think about going up to the mountains, right, the mountains have a lower atmospheric pressure because there's literally less atmosphere sitting on top of you. This is why, water will boil at a different pressure higher up in the mountains because, it will boil at a lower temperature higher up in the mountains because there's less atmospheric pressure. Okay, so the way that we can measure the atmospheric pressure is that, we can get this pool of mercury, we sit our evacuated tube upside down into it, and the atmosphere presses down on the mercury. And when it presses down on the mercury finds somewhere to go and it travels up into the evacuated tube. And the distance that it will travel at a given elevation is 760 millimeters. That's how high this mercury will travel up into this tube. So we say that atmospheric pressure is 760 millimeters of mercury because it's literally how high into this tube the mercury will travel at when it's experiencing atmospheric pressure. Okay, so 760 millimeters of mercury, right? That is atmospheric pressure. Okay. This was developed by Torricelli. So, when you discover things in chemistry, sometimes you get to name them after yourself. So he said, rather than calling this millimeters of mercury, let's call it torr. So that's why you'll see we have also 760 torr. Millimeters of mercury and torr are the same thing. They're just different units. Okay, so he did this to measure atmospheric pressure. So we will call this also 1 atmosphere. Okay, so far we have 760 millimeters of mercury is the same as 760 torr, which is the same as 1 atm, right? All of these things are equal to each other. Around the same time, a guy named Pascal was working on a similar method, and he measured in his units that atmospheric pressure was 101,325 pascals, or 101.325 kilopascals. Okay, so that's another one that we can use, 101.325 kilopascals. Okay, so all of these things mean the same. They are all atmospheric pressure. We also have inches of mercury and PSI, right, pounds per square inch. These ones we won't use as much. The ones that I have circled are ones that you need to memorize. You need to know 760 torr is equal to 760 millimeters of mercury, which are all equal to 1 atm, which is the same as 101.325 kilopascals, or 101,325 pascals. Okay, all of these are the same, and we can use these equalities to convert between different units of pressure. For example, if we had 475 millimeters of mercury, and we needed to express it in atmospheres, which is really common. We're going to use atmospheres for most of our gas gas calculations. So you can do a quick little train track. We have 475 millimeters of mercury. And we know that, from the last slide, we had 760 millimeters of mercury is equal to 760 torr is equal to 1 atm, which is 101.325 kilopascals. Okay, so millimeters of mercury has to cancel millimeters of mercury, so we're going to put this on the bottom. And we're trying to find ATMs, so ATMs will go on the top. Since these are all equal to each other, we can just kind of pick and choose which ones we need to use in our conversions, which is really handy. So now we've got millimeters of mercury canceled. We're left with atmospheres, which is what we're trying to find. Multiply the top, divide the bottom, and you'll get 0.625 ATMs. Okay, so let's try another one. The pressure of a tire is measured as 800.4 millimeters of mercury. What is the pressure in kilopascals? So we start with 800.4 millimeters of mercury. Again, millimeters of mercury has to cancel millimeters of mercury down and to the right. So 760 millimeters of mercury will go on the bottom. And we are trying to find kilopascals. So kilopascals will go on the top. That will be 101.325 kilopascals. So again, we didn't need to convert to ATMs or to torr. We're just going to use whichever units we need to do this conversion because they are all equal to each other. So this gets us 106.7 kilopascals. Okay, so that's how we can do these pressure conversions. So other ways to measure pressure is a manometer. So we have two different types of manometers that we can look at. One of them has a closed end here, and this is under vacuum, kind of like the vacuum that we were talking about earlier. And we'll start with our mercury levels being equal. And then when I open, this stopcock here, and I let in some gas, then I can open this other stopcock and measure the pressure of the gas. And we'll measure the pressure of the gas by looking at the change in height of the mercury. So we'll take the height from one side and the height from the other, and we will look at the difference between them, and that will tell us the pressure of the gas. So again, this will be measured typically in millimeters of mercury. You could also measure it in inches of mercury, but typically it's millimeters of mercury. Another type of manometer is one with an open end. And so this just, instead of using a closed end and a vacuum, this will use atmospheric pressure. And so again, we're going to, open our stopcocks, fill it up with gas, and if our mercury levels are equal, that means that our atmospheric pressure is pressing the same amount that our gas is pressing, which means that our pressure of our gas is equal to our atmospheric pressure. If the mercury is closer, right, if the gas side is higher than atmospheric side, that means that the atmospheric pressure is higher than our gas pressure. Okay, so then the way that you would calculate this is you would calculate it as your gas pressure is equal to atmospheric pressure minus the change in the height. The opposite is also true. If our atmosphere side is higher than our gas side, that means the gas is pressing more, right? The gas is a higher pressure, it's pressing more on that mercury than the atmosphere side. So then we would measure this as gas will equal the pressure from the atmosphere plus that change in the height. So these are manometers, different from barometers. We have a barometer in the lab at COS, which is really handy. Most times now this is just done digitally and something will tell you what the pressure in the room is. Okay. Now we're going to get into some gas laws, and these gas laws will describe the behavior of the gases, and we can use them to do calculations, which is always helpful in chemistry. So this is Robert Boyle, and he came up with Boyle's law. And he says that the pressure of a gas is inversely proportional to its volume. And this will be at constant temperature and constant amount of gas. So we're not changing the temperature, we're not changing the amount of gas particles in there, we're just varying the volume and seeing how that impacts the pressure. And what it means by inversely proportional is that when pressure goes up, volume goes down, or when pressure goes down, volume goes up. So they do the opposite thing. That's what we mean by inversely proportional. So if we think about pressure times volume as being a constant, that allows us to think about it this way. And if it's always equal to a constant, then we can set it up like this, where the pressure and volume of one condition will equal the pressure times volume of another condition, okay? Because we're saying the pressure times volume is going to equal a constant. This will allow us to see if we have initial conditions of pressure and volume, say we change the pressure, we can see what impact that has on the volume. So P1 V1 is equal to P2 V2. This will be the first of our gas laws. And we can see this if you were to collect some pressure and volume data. Here's our pressure in inches of mercury and our volume in inches cubed. If we multiply them together, after we collect all this data, you'll see that it's always a constant, okay? And it's not always 1400, it just happened to be in this example, but it's always going to be a constant. So as we increase our volume, we are decreasing our pressure, because pressure and volume are inversely proportional. So remember, pressure is caused by the molecules striking the sides of the container. If you decrease the volume, right, if you make it smaller, so here in this picture, we have a 1 kilogram weight here, and instead in the next one, we put a 2 kilogram weight. So we made our container smaller. Remember, we're not changing the temperature, we're not changing the number of particles, we're just changing the volume. So here we have a larger volume and then a smaller volume. And what happens when you decrease the volume of the container with the same number of particles, then you will have more molecular collisions that will happen in a given amount of time. Okay, so as you make the walls, the sides of the container smaller or closer together, you're having more collisions, which will increase the pressure. So like you saw in the last slide, the gases are compressible. And the reason that they are compressible is because there's a lot of unoccupied space in the structure of a gas, right? Those gas particles are really, really far apart. And since there's all this unoccupied space, you can squish the molecules closer together and compress them. Again, when you compress them, though, you are increasing the pressure, which is why, oxygen cylinders, carbon dioxide cylinders tend to be under a lot of pressure because they contain a lot of gas particles in a small volume. So a change in pressure causes a change in volume, or vice versa, right? You can have a change in volume that's causing a change in your gas pressure. And if we think about, this next question, what happens to the particles when an external pressure compresses the gas volume? So when we have an external pressure, like before when we changed the weight, those particles are getting closer together, right? They're becoming compressed, and that means that there's a higher pressure of the gas itself. And liquids and solids aren't compressible because those particles are already as close together as they can get, right? They haven't had enough energy to overcome those intermolecular attractions, so they're still close together, so we can't compress them any further because there's not all of this empty space between the particles like there is in a gas. Our next gas law that we are going to look at is Charles' law. So we have Jacques Charles. He was also known for isolating boron, which is super cool, and he studied gases. He was a balloonist. And he said that volume is directly proportional to temperature. And what this means is that when volume goes up, temperature goes up. Okay? And this is at constant pressure and constant amount of gas. So the only thing we are varying is our temperature and our volume. So it would also mean that as volume decreases, temperature decreases. And our graph of volume versus temperature is a straight line. They have a straight line relationship. So as temperature increases, volume also increases. But again, this needs to be in Kelvin. Okay, so you're going to take your Celsius temperature, you're going to add 273, and you're going to do all gas law calculations in Kelvin. Okay, so our ratio of volume versus temperature is constant. So just like we saw in the last gas law, if we have pressure and volume as a constant, then we could set two conditions equal to each other. So here we have volume over temperature is constant because of this directly proportional relationship. So we can say that V1 over T1 is equal to V2 over T2. So our conditions before are equal to our conditions after because it's a constant. Okay, and we can use this to find an unknown volume or an unknown temperature after varying the volume or temperature from our initial conditions. So if we plot our volume versus temperature, we are always going to get a straight line. Okay, but you'll notice they all have one temperature in common down here. So this is in Celsius that it's being plotted, and this spot that they have in common, this is negative 273 degrees Celsius, which is also known as 0 Kelvin. Okay, 0 Kelvin is called absolute zero. And this for now is a theoretical temperature. We've not quite reached it yet, but absolute zero or 0 Kelvin is the temperature at which all molecular motion would stop, right? We know that gas particles and liquid particles and solid particles are always in motion. They are always moving. But our 0 Kelvin would be the theoretical temperature at which all motion would stop. Okay, that is why all of these lines are going back to negative 273 degrees Celsius. It is the lowest possible temperature. It can't go below that, which is really cool. Okay, so if we think about Charles' law from a molecular perspective, if we had a balloon, right, and we filled up our balloon and then we stuck it in some ice water, okay, the ice water would cause those particles to cool down, and we know that our temperature is directly related to our kinetic energy. So if our particles have a lower kinetic energy, this means that they are moving slower. Okay, and when they are moving slower, they are going to collide less frequently with the sides of the balloon. And when they can collide less frequently, that means we're having lower molecular collisions. And remember, we're always going to use our collisions to think about pressure. So less collisions will be less pressure. So the lower the temperature, the less frequently those particles will hit the walls of the container, which means that we will have a decreased pressure on the inside of the balloon. And since we are going to assume the pressure inside the balloon is equal to the pressure outside of the balloon normally, when this happens, that balloon will shrink. So if you stick a balloon in ice water, it will shrink. If we do the opposite and we stick our balloon in boiling water, right, that boiling water will cause the molecules to start moving faster. And as they start moving faster, right, they will hit the sides of the container more frequently, which will cause the balloon to inflate because we're having a larger pressure inside the balloon than there is outside the balloon. So the balloon will get bigger. So we can use this whole Charles law, right, the V1 over T1 equals V2 over T2 to start looking at these changes in temperature to see how they are impacting our changes in volume. Okay, so when I was talking before about our atmospheric pressure versus our gas pressure, this is kind of what it looks like. So if we blow up a balloon normally, the pressure inside the balloon will equal the pressure outside the balloon. But if we heat up the gas particles, right, if we heat up the gas particles, they start to move faster. And when they start to move faster, they are going to hit the walls of the container more frequently. When this happens, that will cause more pressure, right? More collisions equals more pressure, and that gas will then expand until it reaches a point where the pressure inside will again equal the pressure outside. That's how we know how big essentially our balloon is. Okay, so again, if we heat up our gas particles, right, they're going to start moving faster. When they move faster, we'll have more collisions, which means more pressure. So pressure will build up inside our balloon. And the way that it will, relieve that pressure, the balloon can expand, and it will expand until the pressure of our gas equals our atmospheric pressure again. So that tells us how much the balloon will expand. If, say you keep heating it up or you keep, inputting particles, right, at some point, if our, our pressure of our gas can't equal our atmospheric pressure, that's when your balloon pops. Okay, our next law is Gay-Lussac's law, and he said if the number of particles and volume are constant, then pressure and temperature are directly proportional. Okay, so if we are not changing the number of particles, not changing the volume, we're just looking at pressure and temperature, that means as temperature goes up, pressure goes up. If temperature goes down, then pressure goes down. So they are directly proportional. So that's why we have this relationship here. Our pressure and temperature before are going to equal some constant. So we can set our pressure and temperature before equal to our pressure and temperature after to mathematically calculate changes in temperature and pressure. Okay. So all of these gas laws, right? The Boyle's law, Charles' law, Gay-Lussac's law, there's lots of gas laws. And the good news is that you don't have to remember all these individual gas laws because they're all contained in this, this combined gas law equation. This is the one that you need to know. You have to know this equation. So this is P1 V1 over T1 equals P2 V2 over T2. And I say, no, that's not related to R2D2. Just because, you know, kind of sounds like it. Anyways, P1 V1 over T1, P1 V1 over T1 equals P2 V2 over T2. That is the combined gas law equation. And the reason it's called the combined gas law equation is that all of our gas laws are combined in this equation. So if we were to, you know, want to use Boyle's law, then we just get rid of the temperature on the bottom. Boom, Boyle's law. If we were to get rid of our pressures, then there you go. That's Charles' law. If we were to get rid of our volumes, then you have Gay-Lussac's law. Okay, so in any of these cases, if, you know, say, like in this example, if volume was being held constant, then we just remove it from our equation. Or you could put in whatever the constant volume is. But if volume is being held constant, we'll remove it from our equation, and then we have Gay-Lussac's law. Or if, you know, pressure was being held constant, then we would remove it from our equation, and we have Charles' law. So we have all of these individual gas laws, you know, together in this combined gas law. So we don't need to know the individual gas laws themselves. So this will be used when the conditions of a gas are changing. We'll have a lot of different gas laws that we come across in this class, but this will be when our conditions change. So you have an initial pressure and a final pressure, or an initial volume and a final volume. But when we're seeing what the changes to these variables, the impact they're having on the other variables. So here's an example of how we might use this problem. This is the combined gas law problem. It says a sample of helium gas has a volume of 0.180 liters, a pressure of 0.8 atms, and a temperature of 29 degrees Celsius. What is the new temperature of the gas with a volume of 90 milliliters and a pressure of 3.2 atms? Okay, so we have a lot of different variables going on, but the way that this will cue you into the fact that this is a combined gas law problem is that we have two separate volumes, we have two separate pressures, right? We have an initial temperature and we're trying to find our final temperature. So this is showing us that the conditions are changing. That's how we know that this is a combined gas law problem. Okay, so the first thing that I would do is go through and figure out all of your information. That is how I always start these word problems, is figure out the information that's contained in them. So we have our initial pressure of 0.8 atmospheres and our final pressure of 3.2 atmospheres. I would do the volumes I put in milliliters here. It doesn't matter as long as they are the same. You can do them in milliliters or you can do them in liters, but it doesn't matter. Just make sure you're being consistent. So I changed this 0.180 liters to 180 milliliters to use it in these calculations. And then remember, our temperature must be in Kelvin. Okay, so we'll take our 29 degrees Celsius plus 273. That will get us our temperature in Kelvin. Okay, so after we've got this all set up, now we can go about calculating our answer. So we have our equation here. So we have P1 V1 over T1 equals P2 V2 over T2. The first thing I would always do when you're solving these types of problems is to cross multiply. And I would wait, just as a side note, I would wait to plug in any numbers until the very end. I have found that people make the most mistakes when they start just trying to plug numbers in at the beginning, and they lose track and they lose, their sig figs, and all kinds of interesting things happen. So I would always, rearrange your variables as letters and then plug in the numbers later. So the first thing I would do is to cross multiply to get rid of the temperature out of the denominator, because you're trying to solve for T2 here, and we can't solve it if it's in the denominator. So you would cross multiply, so you get P1 V1 T2 equals P2 V2 T1. And then you can go through and you can rearrange for T2, right? You can divide both sides by P1 V1. And when we do that, right, that leaves T2 by itself. So we get P2 V2 T1 over P1 V1. And then we can plug in all of our numbers, right? Multiply the top, divide the bottom, and you'll get your answer. But it did ask for our answer in Celsius, not in Kelvin. So we need to subtract 273 to get our answer back to Celsius. Please make sure, again, that you're keeping track of your significant figures throughout this whole thing. Sometimes it gets a little bit tricky. Let's try another one. So we have another practice problem. This has a balloon with a volume of 785 milliliters on a fall day. Temperature is 21 degrees Celsius. In the winter, the gas cools to 0 degrees Celsius, and it wants to know what is the volume of the balloon. So our first thing that we would do is we would, figure out all of our variables. But you will notice one thing in this problem, and this problem only has volume and temperature. There's no pressures in this, in this equation. So when we think about P1V1 over T1 equals P2V2 over T2, now we don't need our pressures, right? Because our pressure, if it doesn't say anything about our pressure, we are going to assume the pressure is held constant. And in this case, it would be, right, because we're at atmospheric pressure. So we'll just go ahead and get rid of those pressures here. So now we just have V1 over T1 equals V2 over T2. This is a Charles law problem. Okay, so we'll go ahead and we'll look at all of our information. So we have V1, right, our initial volume is 785 milliliters. Our T1 is 21 degrees Celsius, but we can't use it in Celsius, so we'll add 273. That gets us 294 Kelvin. And our V2, we don't know. We're trying to find that. And our T2 is 0 degrees Celsius plus 273, which gets us 273 Kelvin. So again, we have V1 over T1 equals V2 over T2, and we're trying to solve for V2. So we need to get V2 by itself, so we'll multiply T2 by both sides, or you can cross multiply like we did earlier. When we multiply T2 by both sides, that gets rid of T2 on this side, and V2 is by itself. So I'm going to go ahead and flip it just because I like to look at my variables on the left. So V2 is equal to T2 V1 over T1. So our T2 was 273 Kelvin. Our V1 was 785 milliliters. And our T1 was 294 Kelvin. So we can multiply that out, and we get 729 milliliters for the balloon, which should make sense, right? Because our T2 is a colder temperature, right? And we know at colder temperatures, our molecular motion slows down, right? We have less pressure, and when we have less pressure, that will cause us to have a smaller volume. So our balloon shrinks in the wintertime. So that's it. That is the first part of Chapter 5. Go ahead and work on those chapter lecture worksheet problems. Get some practice. And as always, send me any questions you have, and I will see you next time.